Quantum mechanics is more than 100 years old. That sounds like it's the stuff of dusty textbooks, but research on quantum mechanics is more active now than a century ago. That's because many rather elementary facts about quantum mechanics couldn't be experimentally settled until the 1980s. But then, by the year 2000 or so, experimental progress had totally transformed the field. Today, it's developing faster than ever. How did this happen? Why does it matter? And what's quantum teleportation?
Hi, my name is Olivia Lanes from IBM Quantum, and I'm here today to celebrate and explain the relevance and the excitement around the 2022 Physics Nobel Prize. So, just a few days ago, the Physics Nobel Prize for this year was awarded to three gentlemen, John Clauser, Elaine Aspect, and Anton Zeilinger. These gentlemen won the award for groundbreaking research and experiments in quantum mechanics. And all of this research was based upon some original experiments that were done by a gentleman named John Bell, who tragically passed away before he was able to see a Nobel Prize or something of that magnitude. But we're going to discuss it here today and show why the experiments that were built off of John Bell's original theorem are so important. So we have to go back a little bit in history in order to set the stage and the context of why this is so important. So in the 60s, John Stewart Bell was reading the EPR paper, which was a paper written by Einstein and some of his colleagues explaining how they believed that quantum mechanics was an incomplete theory. Now, in quantum mechanics, we say there exists this thing called the wave function, which describes all of the properties of your quantum system, and upon measurement, it collapses into a single quantity that was only described probabilistically before you measured it. Anyway, in the paper, Einstein said that quantum mechanics must be an incomplete theory because this could not be possible. This would necessitate things that he could not believe to be true. And so we were either missing something in the theory. Somehow these particles were interacting in a way that we didn't actually understand or didn't have a description for yet, but basically it was not finished. And sometime later, John Stewart Bell was reading this paper, and he sat down and he wrote what is come to be known as Bell's theorem in just a few lines of algebra. He showed that if you only assume two things, those things being local realism, locality, meaning you can't travel faster than the speed of light, and realism, which means that things have definite values whether or not you measure them. So for instance, we always say if a tree falls in the forest and no one is around to hear it, does it make a noise? If the answer is yes, this would be an example of definite realism. So he assumed only those two things in his mathematical derivation. And he was able to show that there are certain quantities that you can measure that are bounded by classical physics if you assume only local realism. And essentially, he was able to show, on paper at least, that quantum mechanics was incompatible with any classical theory. So anything that was basically including local realism could not possibly work with quantum mechanics. So now, a few years later, John Clauser came along, and he was reading Bell's theorem, and he thought that this should be something that was able to be done experimentally. So he was able to actually perform an example in the laboratory for the first time, a violation of this equality, and show that, indeed, nature behaves as weirdly as predicted. And so, in essence, Einstein was wrong in his EPR paper. And this led to groundbreaking work later on from Elaine Aspect, who was able to perform even more tests of Bell's inequality and close some of the loopholes, so to speak. And then this led to Anton Zeilinger, who was able to show the demonstration for the first time of quantum teleportation, which is not what you might think. It's not at all like Star Trek. People are not teleporting across the room. But instead, quantum teleportation is a way to entangle or correlate quantum particles in such a way that you can transfer quantum information from one to another.
It is actually quite an interesting phenomenon that the general public is so much excited about quantum physics. This comes, I think, from the fact that quantum physics tells us that some of our everyday way how to look at the world are wrong. What is wrong is the assumption that, for example, every object has to be at a definite place at any time. This is not true anymore. Some people say that a particle can be at two places at the same time, which again is not good language. The good language is that there are situations where it is completely undefined where the particle is, and it's not even us who do not know, but the particle itself also does not know, so to speak. So this is an objective non-existence of a feature of reality. And that is new in quantum physics. That does not exist in what we call classical physics, the physics before quantum physics. It is also not true in relativity theory, by the way. There we also have a well-defined space, a well-defined time, well-defined locations, and this kind of objects. This is one thing. The second point is that we, in our everyday view of the world, or in classical thinking, we always believe that for whatever happens, there is a cause. There's an individual cause for individual events. Like when a stone hits me on the head, I know somebody has thrown it at me or something like that. Now in quantum physics we have learned that this causal structure, as we call it, exists on the level of large ensembles, but not always in the case of individual events. Like for a radioactive atom, it is defined how many atoms will decay within, say, the next minutes, but it is absolutely undefined, and there is no causal explanation why a specific atom decays now. So this is another interesting message from quantum mechanics: is the limit of causality in very specific situations. But I should say that many public presentations or discussions make the mistake that they abandon these ideas in general. This is not true. One has to be very cautious when this happens. The third point, which I would like to convey, is that we can have a situation where two systems separated by a large distance are connected in a very new way. This is called entanglement, intrication in French. It simply means that if I have two particles which collide, interact with each other, and they fly apart, if you just imagine like billiard balls, two billiard balls fly opposite, two quantum billiard balls would also fly opposite, but it would be undefined in which direction they fly. They fly in all these directions at the same time. But when I make one measurement, I observe this particle, for example, here, and then the other one at that moment changes its state from being possibly everywhere, only being at this place. And it is wrong to assume that I just reveal where they were before, and I did not just know it. No, the particles themselves also did not know. There was no well-defined feature. So to me, these are the general properties of quantum mechanics. In a more technical language, this is related to superposition, to the fact superposition means that the various possibilities are superposed in a new kind of description, which we call the quantum state. Superposition of the quantum state is the general feature in that situation. And I should also mention that in my personal conviction, these phenomena are not limited to small systems. So far they are, but this, in my eyes, is a technical issue, and I hope that future bright young people will have the possibility to observe such phenomena also for very big objects.
That's all well and good, Craig, but how can something so insane sounding be true?
Well, maybe you just don't understand it. I don't understand it.
Well, why is this stuff so hard to understand?
When people ask me about these things, I always give the same answer. Our neural wiring, the thing that we inherited from our ancestors, and I don't mean our ancestors, our grandparents, I mean, the worms in the muck through evolution. The neural wiring that we inherited was not built for quantum mechanics. It was not built for higher dimensions. It was not built for thinking about curved space-time. It was built for classical physics. It was built for rocks and stones and all the ordinary objects, and it was built for three-dimensional space. And that's not quite good enough for us to be able to visualize and internalize the ideas of quantum mechanics and general relativity and so forth.
But I would like to add a point which is very important for me. When one talks about these things, people very often get associations with strange esoteric ideas and so on. Everything is the wholeness of everything. I don't believe in that. What I'm talking about are specific scientific questions, which can be answered, I hope, by scientific investigation by future generations. And I hope that I'm still alive and somebody has a really good new insight.